Okay, we're recording. We're recording. Let's get to Sketchpad, and before we do that, let me find a charger. Excuse me first. Okay, back to Sketchpad. This was from when I last did it. It was really bad, so I decided to film it again. Hopefully, it will be better. Okay, there we go. So to start off, have you ever wondered how a nucleus is held in shape despite its tiny size? You know, a nucleus is made of pluses. The protons, they have a plus charge. So they're made of many protons, depending on which element you're talking about. Okay, now we have six protons here, right? And inside this nucleus, there are another thing. And this is the neutrons, and they're just kind of they're just in there like a basketball lump. Yeah, it's and around this nucleus there is an electron, not to scale, but it's very tiny. It has almost no mass compared to the nucleus, and this thing, the electron, which is a negative, goes around. It goes all over the place around this nucleus at the speed of light. So it goes very fast. But if you examine this carefully, you'll notice that a mistake, right? A mistake is kind of being made here. You may ask if a nucleus is only made of positive and neutral particles, that positive and positive is going to repel away from each other. And supposedly, if the neutral is neutral, it doesn't do anything at all, right? It doesn't attract or repel with positive. So by theoretically, a nucleus should fall apart because protons are always repelling away from each other. That's by electrostatic force. And we have learned that in earlier years. That is partly true because there is another force in the universe that holds a nucleus together. And we're getting into it. This force is called the strong nuclear force. A strong nuclear force occurs between the nucleons. Now, a nucleon is basically anything that is inside the nucleus. So that will only be including two things: the protons and the neutrons. You know, there are only two things in the nucleus, right? It's a force between. It could be between a plus and a neutral. It could be between a plus and a plus, or a neutral and a neutral. Now, this force does not repel. It holds the particles together. So it does the opposite of electrostatic force when there are two pluses. When the two pluses are pushing away from each other, the same force, the different force, there's a different force that's pushing them at each other. And they're just pushing away like that. Now, when these two forces reach an equilibrium, that means a atom structure is very stable and it won't decay and turn into something else or just fall apart. So um, the strong nuclear force, just an interesting fact here, it is the strongest force that humans know in the universe. Yeah, I mean, it's something that fights against electrostatic force, so it's very strong. And this force has a working distance. It's not like magnets, you just press two ends together, they stick together unless you put them apart. That's not how it works. They have a working distance of 1.0 to 2.5 times 10 to the power of negative 15 meters. If the two particles are too close, say a proton and a neutron, if they're too close, um, the force will repel the two nucleons from merging into one particle. So this time, if they're too close, the strong nuclear force will actually be pushing them apart. But when they're just in the right distance from each other, say there are 2.5 meter, uh, 2.5 times 10 to the power of negative 50 meter in between these two particles, the force will be attractive. It will be keeping them just in the right distance for each other, and not too far away, not too close. When they're too far, the force doesn't do anything at all. Okay, now the last thing we're getting to today is the nuclear, the electrostatic force increases as the number of protons is increased. Say you have an element with two protons. Now the electrostatic force for that element is not going to be very strong. But say now you have 82 protons. Proton number. The electrostatic force in this is going to be very strong. So you have 82 protons, all positive inside a nucleus. They're all trying to pushing each other apart. Now what's going to happen is that this force is going to be so strong that there needs to be more numbers of neutral neutrons inside the nucleus. There needs to be enough attracting forces to keep this nucleus in place, in structure. Since these are pushing with like massive power. Now, to illustrate this visually, we have a n to v, that's not very good, an n to v graph. N on the y and v on the x. Now, n represents the neutron number, and z represents atomic number. If there are one neutron for each proton in a nucleus, which is the case for any elements with under 20 atomic number, the graph will look like this. So it's pretty much diagonal. This means that for each proton there will be one neutron. But since we have learned that after a certain distance on this graph, after a certain number of protons, the electrostatic force becomes huge, that there needs to be more neutrons to hold this together. So the graph will start looking like this. It starts to go a little more slanted, it just keeps going off track like that. Now you can see by the end, for say 82 protons, there needs to be like 140 neutrons. Now this will be approximately the correct scale, but it's not to scale. This is just to give you an idea of the relationship of neutrons as the atomic number is increased. As you can see, I'll be keep doing the diagonal line here to show you how the deviation, that's an increase in electrostatic force, had on strong nuclear force. And that's all we have today. Simple stuff. Just need to keep going back there and revise knowledge till you actually learn it.